Hi everyone, I'm Xulong Tang from the University of Texas at Dallas. Today I'll present our work, personalized dance synthesis based on physical and cognitive intensities. Dance-based exergames have become mainstream because they combine social interaction with physical activity. Commercial titles like Just Dance, Dance Central, and Zumba Fitness attract large user bases and demonstrate how dance can motivate people to exercise through entertainment. Dance is not only physical exercise, it also engages cognitive processes such as memory and sensory motor coordination. With affordable motion tracking devices like depth camera, many exergame systems have explored evaluation, rehabilitation, exertion games, and interactive choreography. However, most systems do not explicitly control both physical intensity and cognitive difficulty. The teaser highlights our key capability. We can control physical and cognitive intensities, and we can also constrain specific joints. Here we suppress right arm motion to support injury-aware routines, while maintaining comparable overall intensity. We begin by randomly initializing a dance using dance segments sampled from a curated dance library. The initial sequence is then iteratively refined through an optimization procedure. At each iteration, the system evaluates candidate moves based on weighted combination of constants, including duration, transition smoothness, motion variety, and physical intensity. The optimization process continues until a threshold is reached. To support controllable synthesis, we build a large dance segment library from public mocap dance datasets. This includes the AIST++, LOZG dance, and also the fun dance. We unify different motions into the simple format, normalizing coordinate system and face interaction. Resemble all motions into 30 FPS, and remove noise frames through an automatic pipeline and also with a manual verification. We segment sequences into 4-second clips, which roughly correspond to choreographic phrases in real life. The final library contains 38.5 hours of motion across 25 genres and over 34,000 segments. We define a dance routine as a sequence of segments sampled from the library. Each segment contains poses represented by 3D joint positions and joint rotations. Our goal is to find a routine that minimizes the total cost, which is a weighted sum of duration, transition smoothness, variety, and two intensity costs based on translational and rotational kinetic energy. Duration cost ensures the routine matches the desired length, and transition cost focuses on segment boundaries and penalize large joint displacement between the last pose of one segment and the first pose of the next segment. This will improve the smoothness. As shown in figures, when disabled transition terms, the generated dance tends to be jumpy, which prevented participants from completing the movement and consequently confounded both heart rate and dynamic time warping distance measurements. Variety cost controls global diversity across the routine. Higher diversity typically reduces repetition and increases cognitive load. Intensity is modeled via translational and rotational kinetic energy, providing an interpretable kinematics-based proxy for physical exertion. We solve this as stochastic optimization problem using reversible jump MCMC guided by simulated annealing. At each step, we propose to remove, add, or replace a segment. Then a segment moves according to a Boltzmann-like objective. Early iteration explore broadly, and the later iteration refines as the temperature decreases. We stop when the cost stabilizes. In our implementation, generating routines for our study settings takes about 51 seconds on average. To evaluate the framework, we build a Unity-based exergame with a Ventrobot depth camera and Polar H10 heart rate sensor. User rehearsing a training phase and then performing a performance phase by following a virtual guide, this purple robot, and the prompt guide, this gold robot, and we'll compute a DTW distance for the feedback. In the training phase, you can see we have a user avatar reflecting the user's motion. In the performance phase, notice that the user is trying to follow the purple robot, which is the virtual guide, and the gold robot in the corner is prompt guide. Feedback is shown as a text animation. We conducted a 20 participants within subject study. First, participants complete the training session to familiarize themselves with the system and gameplay mechanics. After the training session, the participants complete 8 conditioned dances, consisting of first learning dance by watching virtual guide to help with memorization, then performing it. Participants follow a 2x2x2 design, varying intensity, variety, and where the transition term is enabled. The ordering of the dance conditions was set using a Latin square to mitigate all the effects. Participants were given a 5-minute rest period after each condition to prevent fatigue and reset their heart rate. And they were asked to complete the survey. We measure physiological response performance error, smooth ratings, and enjoyment. Here's the result. In the figure 6, it's the visualization of different chaining goal dances with joint level intensities normalized across joints and mapped to a color scale. Figure 7 shows mean dynamic time warping distance across participants. Figure 8 shows participants' ratings of the dance movement. Table 2 showed enjoyment ratings based on the physical activity enjoyment scale. Based on the result, here are the main findings. First, our intensity proxies are meaningful in practice. The sum of translational and rotational energy strongly correlates with heart rate, and intense routines keep participants in vigorous heart rate zones for most of the routine. Second, our variety control affects cognitive difficulty. Higher variety correlates with larger DTW error, indicating harder memorization and execution. Third, enabling transition cost significantly improves perceived smoothness. Finally, participants reported higher enjoyment with an average PASIC score of 85%. Beyond the control study, we demonstrate two practical capabilities. First, we can constrain joint level intensity using a joint mask, which is useful for injury-aware or rehabilitation settings. In this example, we suppress right shoulder and elbow rotation while maintaining high intensity elsewhere. Second, we can vary training goals over time. By alternating intensity targets, we generate an interval training routine with visible heart rate response changes. By alternating variety target, we create segments that are easier or harder to reproduce. Our intensity objectives are efficient and controllable, but they are kinematic space proxies and do not murder forces or joint targets. Since the optimization is stochastic, it does not guarantee exhaustive coverage under a fixed computed budget. Finally, we do not yet enforce beat-level music synchronization. In the future work, we plan to add music-aware cards, explore joint-level recombination core segments, and integrate real-time physiological feedback for adaptive training. Thank you for listening.